Instead of do 5.
Yeah.
Okay, so just to recap, for those of you that are at home, we've got a new postulate that we can use to prove similarity. And if we can prove that two angles in two triangles are the corresponding angles are the same of two triangles, then we can say that those triangles are similar. So that's what postulate 25 tells us. And you will have to, I may give you a problem on a test or a quiz that says that sets this problem up and ask you, are they similar? And you say yes, because of, I wouldn't put postulate 25, because then I'll have to look up postulate 25 and go, what is that? I don't remember what that is. Just write AA, right, to let me know that. So Jackson was claiming, we're all getting ready to bust out laughing here, but he's claiming that he can prove that these two triangles are similar. And so he said they both have 90-degree angles, and then he said, well, now he knows the correct term.
The two angles in the middle are corresponding angles.
Vertical.
Vertical angles. All right, so if you have two lines that intersect like this, these angles here are congruent, and these angles here are congruent because those angles are vertical angles. All right, that's okay. So what you could do, you could label this on a test or something. You could just show me that you knew that those were congruent. And so Jackson's exactly right. Nice job, Jackson. Thanks for letting me pick on you a little bit. So if I ask that question, you would say yes, they are similar by AA. Okay? Everybody got that? Makes sense? Okay. So let's move on to, so that's really all that I want you to take away from section 8.4. Wasn't that easy? See?
Wow.
Now the homework problems are going to let you practice some of the stuff that you've already done previously, but it's basically the same thing, just giving you a little extra practice with that. 8.5, let's move on to a theorem now that also allows us to prove similarity. And that theorem is the side similarity. So theorem 8.2, side.
Mr. Walker?
Yes?
Didn't we already learn this?
Where did we learn side? Yes.
Congruency.
We learned it when we talked about congruency of triangles. We're not proving congruency now, we're just we're proving similarity, right? And so this tells us that we know, when we started talking about similarity, we were saying that the lengths had to be, the proportions of the lengths had to be the same, and that the angles all had to be the same. But now we're saying with the side similarity theorem, so SSS, similarity theorem. Unlike the congruency one here, we're saying that if the lengths of the corresponding sides of two triangles are not congruent, but are proportional.
Big words.
Yep, are proportional. Then the two triangles are similar. So we're not proving congruency this time, we're proving similarity. All right? Everyone understand the difference? And then similarly, see? Similarly, theorem 8.3 is the side angle side, or the SAS, similarity theorem. And as you might expect, that one says if an angle in one triangle is congruent. Why am I writing out the word congruent? I'm supposed to do that. Is congruent to an angle in another triangle, and the length of the sides, including these angles, are proportional the triangles are similar. So it's kind of like the theorems that we've already learned, but again, it's not talking about congruency, it's talking about similarity. So instead of saying that the length of the sides have to be congruent, it says the length of the corresponding sides have to be proportional. But the angle, because with similarity the angles have to be the same, the angles do have to be congruent. Okay? Any questions about that, either of those? Angle, angle, side, 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 or side, angle, side, for proving similarity? All right. Well, this works some problems. Once you guys, looks like you can focus. Man, somebody chowed down up here and didn't clean up. All right. So. They ask us for this particular problem, all right. All right. So for this particular problem here, we're asked which of the two triangles are similar. Now, given the one postulate and two theorems that we have to choose from to try to prove this, which one are we obviously going to use in order to prove similarity here?
Side,
Side, side, side.
We've got to use side, side, side because we don't know anything about the angles in these figures, right? So both of these, angle, angle, and side, angle, side, all include angles, so that's not going to help us at all in this case. So we've got to prove that the lengths of the corresponding sides are proportional, all right? Now, this one, the figures are rotated around, they're not all facing the same way, right? So you're going to have to figure out in your own mind how to orient them, which side corresponds to which. But the nice thing is here, they've given us the value of all the lengths, right? So all we really have to pay attention to is we know the smallest side is the 6 right here, and so that has to correspond to whatever's the smallest side here, right? So the 6 corresponds to the 4, the 12 has the biggest side has to correspond to the biggest side, and the middle one to the middle, right? So in order to prove this one, that these are congruent, then we could say 12 corresponds to the longest side here, which is the 8. And that has to equal the medium length side, which is the 9. And that corresponds to the medium length side here, which is the 6, which has to equal the smallest side, 6, over the smallest side there, which is 4. Do you guys follow that? Did I lose anybody when I wrote that down? I'm happy to go through it again. No? Okay. So do these fractions all reduce down to be the same thing? This is divisible by 4, top and bottom, so that's 3 over 2. Top and bottom here are divisible by 3, so that's 3 over 2. Top and bottom here are divisible by 2, and that's 3 over 2. You guys see that? So clearly these two triangles then, by this theorem right here, are similar. And how would I write down that similarity statement for the two triangles? Who wants to take, somebody that's not on the board? Anybody that's not on the board want to take a stab at that? Aren't you on the board?
Yeah.
You're on the board.
Wait, what's the question again?
Huh?
What's the question again?
I want you to write, since we've proven now that they're similar, I want you to write the similarity statement for me. How would I say this triangle is similar to this triangle?
Oh, wouldn't it be?
It's going to look like this. I just want to make sure you got the letters in the right order. That's my
So it would be triangle ABC.
Okay, so we're going to say ABC. So now the thing she's got to do is make sure that she picks the corresponding point for A and B and then C, right?
It's congruent to triangle DEF.
So she said DEF. Let's see if she's right. She gets her name on the board just for trying, right? So when I'm looking at this, D is between the smallest side and the largest side. Is that the case here for A? It is, right? It's between the smallest and largest. When I look at E, I see that E is in between the smallest and the medium side. And so that's corresponding to B here. And B, sure enough, is between the smallest and the medium side. The other one's automatically going to be correct, right? So if we wanted to orient this one so that it matched this one, so that they were kind of facing the same way, we would draw it like this, and we would say this was E, and this was F, and this was D, and then we could label it 8, 6, and 4, right? And I'll just tell you, sometimes that's really helpful. If you're working a problem like that on the test, just go ahead and figure out which side's the smallest and which one's the longest, and rotate the figure and draw it again on the test so that they match up. There's just kind of less room for error if you do that. Okay? All right, so we've proven that those two are similar. Let's just check the other one. I think the problem asks which two triangles are similar, so I'm guessing this last one's not going to be. But how do we prove that? Is it already drawn is it oriented the correct way? It already is, right? So this one's a little easier for us. So we can just say 12 over 14 has to equal 9 over 10, has to equal 6 over 6, right? So we immediately see this can't be right. 6 over 6 is going to just be 1. None of the rest of them reduce down to 1. So clearly, this one is not similar. Okay? Any questions about how I went about doing that? This will definitely be on your next quiz, like this idea, right? Being able to give you some triangles and then you use one of these theorems to prove they're similar. We get out of here at 2. Yeah, okay, or a little before 2. All right. I saw Mary looking at the clock there, so I gotta make sure she makes it out of here on time. Nothing else? Okay, let's don't do another example yet. Well, let me just set this one up for you, just so you see it. I want to make sure we get through the last section. But for this particular problem, they give us something that looks like this. All right? And they do this. And so we've got S, P, Q, R, T, and we've got 12, 15, and 4 and 5. All right? And the question here is they ask us, is triangle RST similar to triangle PSQ? So is the big outer triangle right here to here to here similar to this little triangle on the top, PSQ? Which theorem are we going to use to prove that? Do we have the length of all the sides?
No.
Can we calculate the length of the missing side?
Yeah. No.
We'd have to have, it'd have to be a right triangle. We'd have to be,
Yeah.
then we could use the Pythagorean case. Yes?
So the very tippy-top angle would be the same for both triangles.
Did you guys hear that in the language that he used? Very technical language. The very tippy top. I couldn't have said it better myself. I like that. The tippy top angle, he's exactly right. This angle, if we draw a big triangle, right, like this, and then we draw a little triangle like this, these angles are congruent. Right? Excellent, Joshua. Those angles are congruent, and so now that opens up the possibility of using this one, because this involves angles, and that one over there. Do we know any other angles are congruent? The answer's no.
I was like,
So we're going to say no, and but what we do know is we can prove using this theorem right here. If we can prove that this side, which is what's the length of this side right here for our big triangle?
16.
16. It's the 12 and the 4 added together, so don't overlook that. The length of this is the 5 plus the 15 added together, so 20. And then the length of this is 4, and the length of this is 5. And so as long as we can prove those sides, since those sides contain our angle, then we can use SAS if 16 over 4, right, this side over this side corresponds to 20 over 5, this side over that side. And actually both of these, clearly, we get 4 over 4, or you can reduce to 4 over 1, right? But we get a true statement, and so we've proven that by side angle side, yes, they are similar. By side angle side. Nope, side. Angle side, sorry. Alright, you guys got it? Alright, let's move on to section 8.6, which is our last. Ooh, it's longer than I thought. Okay. Get ready, we're going to drink from the fire hose. You guys ready? Alright, so we've got a couple of some new theorems. And they are theorem 8.4, and that's the triangle proportionality theorem. Make sure I'm spelling it correctly. If a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. A line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. So what that looks like is this. We have a triangle that looks like this, and we know that these two lines are parallel. then we know that these sides, this triangle here, let me just write it down. R, T, Q, U, S. So for that drawing there, we know that, so if TU is parallel to QS, then RT over TQ equals RU over US. So the length of this side, the proportion of this side to this side is equal to the proportion of this side to that side. Theorem 8.5 is just the sort of the opposite of this, the converse of the triangle proportionality theorem. Which just says the opposite. If a line divides two sides of a triangle proportionally, then it is parallel to the third side. It's just a way to say the reverse of that, right? So I'll let you finish writing that, and then we'll just walk through it real quick. All right, does everybody see how they're just the reverse of one another? So depending on what we were trying to prove, right, if you had a proof that you had to do, we might use it this way, where we know that they're parallel, and so then we could say these are proportional to one another. But if I wasn't told that these were parallel, but we could prove that these were proportional to one another, then we would be proving that these two are parallel. So it's just saying the opposite of it, okay? So there's, let me go ahead and give you theorem 8.6 and 8.7. Theorem 8.6 kind of looks like that a little bit, but different concept. Theorem 8.6 says if three lines, we don't even have a special name for this, all right? So theorem 8.6 says if three lines intersect two transversals, I'm sorry, I left out a really important thing here. If three parallel lines intersect two transversals, then they divide the transversals proportionally. Okay? scoot out of the way here. So notice here I've got 3 parallel lines. We know that because I've got the arrows on here, right? 3 parallel lines intersecting 2 transversals, and what that means is that, based on this theorem here, is that the ratio of this length here and this length has got to be equal to the proportion of this length to this length. Okay? So UW over WY, that distance there, has to be equal to VX over XZ. It's very similar to this guy, right? It's similar in the sense that, you know, this one over this has to be equal to this over this. It's just we're not just dealing with a triangle here. We've got lines that keep going. And then the last statement has to do with bisector. Last theorem 8.7 says if a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other 2 sides. Write that down, and then I'm going to draw it on the board what that means. I'll go ahead and draw the picture because I think the picture is kind of the easier one to see here. So I know that ray CD bisects angle ACB. How do I know that? If I were to just draw this figure on a test or a quiz, how would I know, someone whose name's not on the board yet, how would you know that it bisects ACB? Yes?
Because those 2 angles are the same.
Because the angles are the same, right? So we know it's a bisector because it split that angle exactly in 2. And so what this says is that for a triangle, if that's the case, then that means that these sides here have to be proportional to the other sides. All right, so that means that AD, the proportion of AD to DB, this side to this side has got to be equal to the AC over BC. All right, so this side over this side has got to be equal to this side over this side. Okay? So I know we're pushing for time, but I want to at least work one example to let you see something. One of these theorems in action. Somebody pick a theorem. These are basically the same.
8.6.
8.6. So you want to do this one? All right. So that would be example 3. Let me just. Do I want to make one up? No, we'll do example 3. So example 3 looks like this. So we've got these lines here, and they tell us that. Whoops. so they draw this. And here, what's a little different from the way our theorem is stated, they don't tell us that these three lines are parallel, but what they tell us is that these angles are all the same. And so because those angles are the same, then we know that those three lines are parallel, okay? And so I'm just going to write the values down here. We've got 9, 11, 15, and they want us to find, I'm assuming, TU. So we're just going to label that X. They want us to find that number, all right? And so it's really simple. Once we know this theorem here is true, all we've got to say is that 9 over 15 has got to be equal to 11 over X. All right? The proportion, this right here, this proportion has got to be equal to this proportion. Okay? So we just cross multiply, and we say 9x equals, wow, those are big numbers.
You could just.
I can simplify. We're going to
9
simplify.
15.
Yeah, I like it. So that's 3 over 5. Is that better? 55 equals 3x, and then divide by 3, and x equals
Here, I can.
what is that? That's not, that won't simplify. Just 55 over 3.
Yeah, it is.
Yeah, 55 over 3. I was like, 55 is not divisible by 3. All right. There you go. So that's how you find it. Is that simple enough? All right, so you guys will have some problems that'll give you some practice with this. All right, so you can find this out. Have a great break. Don't break anything, though. And you guys, we'll see you in a couple weeks. Okay?
I'm gonna break a leg. I'll try not to.
Break a leg, but don't break a leg. Thank you.
Break a leg, but like don't break a leg. So get it, I guess.